the question, the topic we were thinking about was topological sigma models and how the Pearson dissipated hydro, though I never able to come to hydro this year. So let me just give a recap of the last part of what I was saying yesterday, which is about Schwinger-Keldysh path integrals. So the essential die in the game was this path integral with double focal, which calculated, which is a generating function of both time ordered and anti-time ordered correlators and mixed correlators of the form that I wrote down yesterday. So there's an initial density matrix, and then you just time evolve it as you time evolve the density matrix. And you deform those evolutions by the draw evolution and the get evolution by two different sources, and that gives you a path integral. So the first thing, one of the important things that we noted yesterday was that in the aligned limit, like that is when J1 equal to J equal to J, then ZSK localizes to something like that. Topological quantity theory of initial coordinate. It just measures various correlations in the initial density matrix. With only the J T equal to 0 matrix, and everything else is cancelling. Okay. And so that was the first thing we noted. Okay. And we also noted that this is also encoded in the sector difference operators. So the difference operators, when it is OR minus OL, so the OR is the correspondence to JR and OL is the coupling to JL, like this. So
let me just clarify this question which even asked yesterday. The OR and OL are evaluated on different contours. That is what distinguishes them. So that's
But as far as path integral is concerned, they are two copies of the fields. They are not part of the
No, I understand.
Yeah. So good. So that is the first thing that we noted. The second thing that we noted was that this quantity of different operators. Is better written in superspace with so let's say sigma A is your usual spacetime. Then to your spacetime you add two coordinates theta and beta bar. Okay, these are Grassmann. Okay. And associated with these, there were translation operators, which is Q, which is then by del theta bar, and Q bar, which is then by del theta. Okay. Which like if you write down some translation invariant expression along these coordinates, then you get a symmetry. Of the action. Okay, so say that the Q of the action is 0 and Q square is 0, and then and such that OR minus OL is Q of something, and that's Q minus.
The Q and Q bar not shifted by derivatives?
At this point, not. Okay. So in general, at this point, not. They will start getting shifted. So let me just say another thing. So then the third thing that I was telling you by the way of scalar example, which I will go through in a moment again, is that to get thermality. So all this is some general stuff for some general density matrix, but we are interested in thermal and near thermal and dissipation in the near thermal systems and so on. Okay, and fluctuating dissipation, etc. encoded if you have, if you convert these del thetas into something like. Gauge the thermal translations in okay, where like you can do it as also go to a gauge where only one of them is there. So writing it.
Sorry, look, what was SQS is equal to 0?
S was that.
And what was E the last time? That's Q bar.
Q bar.
Okay, so the point is that so once you do that, so you can. So let me call this SQS. Okay. So once you do that, so this and d theta bar is going to try to commute so that they actually to some. Something like theta bar.
Is beta to be thought of as constant or a variable?
It's to be thought of as a constant. Beta can be
space sigma. In space.
Okay. But yesterday I was, you can just think of it as a constant for a moment. But eventually I will want it to be a function in a very specific way. Anyway, so we said theta bar. Okay, you can just work out this.
So why wouldn't you absorb beta in A theta?
I'm sorry.
Why wouldn't you absorb the beta, which is a function of space-time, into the gauge field itself, or?
Because I want to show that I want to think of this guy as gauging the thermal translations. So this is the thermal translation.
Beta d by d is thermal translation operator. Okay.
Yeah. So and also beta has an index and so on. It's easier to do it this way. So you get something like this. Okay. This is just an algebra. Take these expressions, calculate the French commutator. So you get this thing, and this evaluates to this point in the sketch. Okay. Anyway, but the point is that like you have, and what we did was basically these three ideas. Okay, we applied to the scalar theory. Okay, which let me just begin by reviewing.
Good way of taking notes is to take pictures of the blackboard. Unfortunately, you just erased it. It was a video. I put it as a video.
If you want to refer to it in the middle of the
All right.
Okay. So the point is that we're talking about scalar theories. So the scalar theory, the single topic theory, okay, or like in case of harmonic trivial systems, you can also call it the Landau-Ginsburg theory, because that's what it is. So there's some relevant field, okay, which describes the problem, and we write down Lagrange for it, okay, which could be like something like.
So okay, all of this is when JL is equal to JR. So you have set the quantum sources to
no, I mean like the sources of the quantum field.
quantum.
Okay. So which are actually classical.
Yeah.
But the point is that I will. Yeah, so let us say that we got it.
I didn't understand that. Why, where have you made that assumption?
Yeah, so the point is that, I'm not quite. Let me just come to it in a moment. Okay, so I'll answer your question also.
You're saying that's the only supersymmetric combination of something. That's
So the point is this, that you know, like, so usually we start with some Loganayagam theory, or some Lagrangian, some field theory, some fields, which describe the system, which kind of describes a part of the non-dissipative dynamics. Okay. Or often, you know, just the statics, okay, of the system under question. So the time, whether, depending on whether the theory is time dependent or time independent, and so on. Okay, and then, you know, like, you want to actually take this theory, which is a kind of which models part of the dynamics, okay, and kind of soup it up, okay. So Schwinger-Keldysh theory, okay. And the kind of questions that, you know, one would like to ask is that, let us say you are given a system which looks like this, you know, statics is described by this kind of free energy functional, if you wish, under this free energy functional. Then what are the possible dissipated, possible dynamics and dissipation that you can have? So this is obviously a very interesting question. That, you know, that so you have a system of static correlators, you know, and they describe this. And often you're interested in the question that if you turn on some source which is slowly time varying, what can you do? How do you classify the response of the system? What are the possible responses of the system? Of a system whose statics is described like this. Okay, what are the things? And the particular strategy that I was outlining yesterday, though I didn't quite explain it elaborately, but that's what I'm trying to do now, is to take this theory. Okay. So let's call it theory or random. Okay. Take this random theory, okay, and take it to superspace. Okay. And what this does is that it automatically does the doubling. Okay. And it also has to go. Which might decouple or which might not decouple, depending on the theory and stuff. But the point is that, you know, you have a doubling transpose. Okay, so that's the first step that you do. And the second step, okay, is dependent on this, which is that, you know, like,
why are they called hosts?
Because they violate field statistics. Okay, so what you have, so what would you do in this theory is that you take this phi and make it into a superfield, capital phi, okay, which has, let's say, this average field phi, and then you have some, and then theta bar theta, and then you have some phi terms.
And the point is your thetas are not space time spectrums.
Yeah, thetas are not the space. Yeah, that. Yeah, in that sense, it's different from the usual supersymmetry, but it's more like a twisted supersymmetry. Okay, so that's what you do. So you take certain theory, you know, the fields that are the effective fields of the static problem. Okay, and you kind of you know, like take it into superspace and make it into superfield. No.
You said everything was supposed to be formalism.
No. So I didn't write down an index.
Oh,
yeah.
No, but since Loga said that it violates its spin statistics, you know, the things that multiply theta are fermions. If they've also spin as it would not violate.
So the point is that, you know, like, so this thing, and now, you know, like, you want to also you can add and inclusive, and, you know, like, so this is the thing, and then you can write down the general possibilities.
So fermions are also auxiliary. integral field is phi and phi diff. If you do Schwinger-Keldysh.
Yes.
The fermions are also auxiliary fields you have used.
Yeah. So to make sure that the part that I rub, which is the topological quantum field theory, is reproduced. So you write down the general possible action in superspace. Okay. So this is in the aligned limit, as we pointed out. Okay. And then, like once you've gotten that aligned limit and this static correlations and so on, once you can reproduce it, and then, take, or move away from the aligned limit.
So, Loga, let me ask you something. Sorry, I'm a little confused. So, the phi average and the phi difference are local fields, or phi left and phi right are at different time points. Separated by which I suppose you're doing formalism. Then this superfield that you have written isn't it a bilocal type of object? I mean, there are fields at different time points here. So what is this object?
So, in the Schwinger-Keldysh, it depends on how you look at it. In some sense, you don't have a beta separation. Okay, and the point is that you have a certain identification, okay, which is how this is, and at least in the aligned limit when phi difference is equal to 0, okay. So another way of saying it is that though they live in two different guys, okay, in the aligned limit there's a sense in which they are living in the same space, okay. And then you can do these things. Okay. And what I'm trying to do is to think about the limit where they are not aligned. Okay. As a small deviation from the aligned limit. Okay. And that's what I'm trying to do. So move away from JL equal to JR. Okay. By adding some JL minus JR. So how do you do that? Okay, so for example, in the static case, you can add to this term some source for phi, right? Okay. So here, when you do this, you take the J to be an ordinary field, right? And J is just J. Let's say J hat, which is J. This is a field. And the way to do it, the way to move away from the aligned limit is to make the source, to add to the source something. So you basically take J hat to J hat plus to some J minus J hat.
Plus fermionic pieces.
You can also add fermionic pieces if you want, but usually. It's that, if you wanted to calculate the ghost propagator, you would like to add fermionic pieces. Okay. So what this does is that, it gives you, and then, you are taken away from the limit, and this theory, because these are non-dynamical fields, these are actually non-dynamical fields. So in the non-dynamical fields, if you introduce a theta bar theta component, okay, that kind of breaks supersymmetry. So again, if you're familiar with how this works in N=140, one way to introduce supersymmetry breaking or soft supersymmetry breaking in SSE, for example, is to take a field whose theta bar theta component is non-zero. Okay.
And just understand, so the action is J times superfield phi integrated over theta.
Yeah. So the action here would just be like phi square, and this integral has d square theta, and this. Okay. So what this theory does is that at bare minimum, it reproduces the same kind of static correlators and this thing. Okay, so what we have done is that this theory reproduces the same correlators. Okay, we have quite not addressed this question yet, which is about what are the possible dynamics and other dynamics that you can add and dissipated things that you can add and so on and so forth. But at least like what we have done is that we have doubled the theory. Okay, so that we have gone through, we have taken from a Landau-Ginsburg kind of description to a Schwinger-Keldysh kind of description, where you have double the fields and some ghosts and so on and so forth. And this theory at least satisfies all the basic properties of the Schwinger-Keldysh path integral. If you do a path integral with this theory and this superfield, then you can show that in aligned limit it's supersymmetric because everything is in superspace and so on and so forth. And the difference operator decoupled for the same reason. The top components correlators are decoupled in the dependent to supersymmetric theories and so on.
Can I ask a question? I am very confused about some things. So if you don't mind. So this field, this super field that you wrote is actually a bilocal field. Separated by.
Not in the aligned limit.
Not in the aligned limit. You're not really doing the aligned limit for the actual problem. So it's really what I'm trying to get at is that you have introduced the auxiliary gauge field, you see, corresponding to the normal translations. Is the use of the gauge field actually to restore a certain locality to this whole idea of Schwinger-Keldysh? Because you introduce redundant degrees of freedom to usually to have a local theory, and if you eliminate them, then you don't get local theories. Is there some
it's true that you can think of that as localizing, but not localizing exactly this. I'm not in this description I'm not comparing gauge field here, but the gauge field is really taking care of the thermality, which I'm coming to.
You're working with a bilocal field.
It's just broad. There is a.
And just to check about the violation of supersymmetry, Jacob. So supersymmetry will transform phi by d theta of phi, integrate by parts.
But it won't transform the J.
It won't transform the J.
So you're not supposed to transform a non-dynamic.
Exactly. So you integrate by parts, and so if d by d theta of j is 0, then it's supersymmetric. If it's not, it's not.
Yeah.
So Logan, this kind of supersymmetry, it's not really supersymmetry. The psi and psi bar are like realistic ghosts.
Yeah,
right?
they're ghosts.
They're ghosts. Okay. Now, are you saying that even in normal situations where we encounter realistic ghosts, we can always construct a superfield of this kind?
Yeah. Actually, you can do Faddeev-Popov this way. You can do Faddeev-Popov this way. It's kind of, in some sense, it's kind of trivial. If you have some q's which satisfy q square equal to 0, you can always represent as del by del theta in something. Right? You can just.
But I think Gautam's asking is, are these sort of like the B and the C ghosts?
They are ghosts. Okay, they are not
the usual Faddeev-Popov.
They are not Faddeev-Popov ghosts for any particular gauge of variance.
If you did this procedure for ordinary Faddeev-Popov, would the analogs of psi and psi bar be the DC?
Yes. So I can tell you how you should think about Faddeev-Popov in the Schwinger-Keldysh language and this kind of language. See, what is Faddeev-Popov? Faddeev-Popov is basically you have some gauge theory, okay, path integral, okay, and you want to gauge fix it. One way to gauge fix it is to add to a gauge theory a Higgs field, right, and Higgs the gauge, Higgs the gauge invariance, okay. But of course, usually, in the Faddeev-Popov procedure, we don't have a physical Higgs field. Okay. So what you would want to do is you would want to do a Higgs field, but you would want to cancel it away.
Higgs meaning by Higgs you mean fix that field to be a particular value.
Yeah. So the thing is that if you have a Higgs field, if you have a field which is charged under, let's say that joint of that gauge group. Okay.
Go to the unitary gauge.
Yeah, you can go to the unitary gauge. You can and then you would gauge fix it. Or you can gauge fix it whatever way you want. Okay, but in the sense that, so what I'm saying is that Higgs fields are naturally gives you, keeps track of how the gauge fixing works, and the dynamics works and so on. And what you can do is that you can Schwinger-Keldysh this Higgs field. Okay. What do I mean by that? That is that that the gauge theory, in some sense, just has the ordinary fields, whereas this Higgs field is actually a superfield in the sense that I've been talking about. Okay. So it has been Schwinger-Keldysh in the sense that there's a left going and the right going, so it kind of cancels out of any correlator that you calculate. Okay, provided you are in the aligned limit. Okay. Now you can write down such a thing. Okay, you can write down the Higgs field in the aligned limit. Okay, and when all dust is settled, you will see that this gives you the ghost, anti-ghost, some Lagrange multiplier. The Lagrange multiplier field, what is sometimes called the Lagrange-Outram field, and so on and so forth, out of these guys. Okay, so you can understand Fadi-Papo, and the Fadi-Papo is basically. So Fadi-Papo ghosts are in some sense the ghosts and the anti-ghosts of some Higgs field length.
Where does the nature of your gauge fixing condition come into this?
Well,
so what is that the gauge here del of A is equal to 0?
See, that just that just comes out of integrating out things. So this is kind of an option, okay.
But how do you put in what your gauge condition is into this option actually?
How do you put it? For example, you have a Higgs field, right? So you can just go to the unitary gauge of the Higgs field.
That's a very specific. So a particular gauge choice can be thought of in this language. But suppose I wanted to do Lorentz gauge, that would be hard to do in this language.
Well, you can do the Lorentz gauge also. You can do the corresponding, let's say, R psi gauge. Okay, you can fix the R psi gauge in this Higgs field. Any of these two gauges that we've used. You can fix it in this Higgs field. Okay, and calculate
for the Higgs field.
For the Higgs field and its partners. Okay, and what I'm saying is that in some sense after you integrate out this and this guys, you'll be left with just the ghosts of the Higgs. Okay, so you add a Higgs field and kill it. So what remains is only the ghosts.
But what I'm trying to understand is you must set your gauge condition on the Higgs field, not on the original gauge.
Usually you do something like this is different from that, but from D phi. You can put some covariant condition. Right? Like one thing you can do is, for example, if you have a d mu phi the whole square, okay. That gives you, as the mass, so that naturally localizes used to d mu phi equal to 0. If you take this coefficient large. So that would be when the phi is equal to 0, it will just give you some a mu phi equal to 0 phi is constant. Getting a mu phi equal to 0.
There are a lot of conditions.
Well, this is the same condition as this.
Yeah, but doesn't that sound like a very condition? You normally have one gauge condition, one matrix of gauge conditions.
Yeah, so that depends on the rank of phi. So phi for me is an adjoint field. Okay.
Right, so then that's B times as many gauge conditions as you have. That's too much, right?
That is.
You can't set B adjoint condition, B matrix. Well. So maybe we can do the figure with this later.
Yeah. But the point is that there is a way of understanding the usual Fadi-Papo trick also this way. So in that sense, yes. So these are kind of a universal construction which you can use to understand various those constructions. Anyway, but the point is that so you have this. Okay. So the next is of course dynamics. Now, dynamics is usually a very difficult question, because you are kind of asking about, you have to tell more. Okay? And in our case, we will confine ourselves to near thermal conditions. Okay? We are interested in hydro. Okay. So, in general, of course, you can write down various possibilities, and it will have, you have a lot of things in action which will classify the dynamics. But but it's usually sensible to go to a particular situation where you can actually control what is happening. And one way to control it is to say that I'm interested in near thermal situation. Okay. And the real-time situation, the way you do it is that, the way you take care of it is by saying that, like you gauge the thermal transformation. So this is already clear, like in the Euclidean description, at least, where what we do is that, like we take a field and we say, if you thermally translate that field, you get back that field after some sign or something from here. But you get back the field. So the Euclidean field theory already gauges thermal transformations. Okay, and what I'm trying to do is basically do the same thing in the real time field. It's a discrete gauge. It's a discrete gauging, and yeah, it's a discrete gauging. Okay, and you might one way to say is that like it may become like a continuous gauging. So this becomes like a continuous gauging
At long distance.
At long distance for distances much larger than meter. Okay.
For now, the superscript formalism that we introduce is essentially to package the right properties that required for Schwinger-Keldysh. Will you use any of the other things like what identity, superscript, anything like will it be? Will you be using something or like it's just?
It will be built into the formalism. See, the what identities are just the Q invariants of the description, which is necessary for me to reproduce the Schwinger-Keldysh properties. Okay, this topological limit and the dialectical. Okay, but I won't be using it explicitly, but they're all there. Okay, the whole formalism is there, and it is needed. Okay, and the way you do it is basically so let's say what you did here is that you took the space coordinates and you added theta bar to it. Okay, let me call this a zi. Okay, so here you should have let's say you have a gauge field in the superspace. Okay, which gauges these guys. Okay, and as I was showing in the scalar example, this kind of gives you some.
If you have C mod Z, let's say something. I'm thinking of some other discrete gauging, for instance, an overfolding. No matter what n is, no matter how large n is, you don't introduce a gauge field for that. Discrete gauges usually are not associated with gauge fields.
Well, I mean, like if you have some, you can have a discrete gauge field. Just be a discrete gauge field.
A discrete gauge field, and that thing has dynamics of its own.
Yeah. So you have a discrete dynamics of its own.
There's no new degrees of freedom associated with that. The gauge structure. You can maybe say something.
I mean, another way to say it is that like whenever you gauge something, whenever you, this is like more like
your discrete gauge thing is a twist in the time direction. That's what you call it in this way.
So you have twisted sector. Okay, it's not just taking the original theory and just looking at things.
I agree. You have twisted sectors. So that's what you. Okay, so your gauge field should mimic that. Just give you twisted sectors.
Is there a sense in which this thermal translations is a local symmetry?
In the long distance field. Okay. I mean, it is local in a very specific sense. So let me just talk a bit more about it. Okay, how this works. Okay. So what we did was that for you can take a del I, which is one of these ordinate derivatives, and you're doing something like del I going to an AI meter dot n. Which has some timeless vector. Okay, and then you can look at this Gilbert value. This is a kind of so you're gauging the thermal translations, but the question is that what is the kind of representation theory for it? You can try to understand the mathematical structure of this kind of gauge theories and this kind of gauge invariants. For example, PI. Okay, so there are various representations of it. So let's say let me introduce a thermal bracket. Okay, which is like a commutator. What I call a thermal bracket. Okay. Which what it does is that it takes So this is some parameter which does the thermal translation, and it takes a field phi, okay, and it just gives lambda beta dot del phi. All these now should be thought of as just superfields or ordinary fields. It doesn't matter. But
so you're promoting a local translations by beta into an exact symmetry of your dynamics.
yeah,
Is it clear that should be the case? I mean, I know it's an approximate symmetry this is symmetry in the static situation. So when beta is varying like this, is it clear that should be an exact symmetry, not just something approximate?
okay. So let me. The question is about having dynamics. Okay, and let me add the dynamics. Yes. So the point is that so you have, let's say you introduce this. So this is a field which turns out like this. Okay.
Sorry, one more question. The fact that it's in imaginary direction is dealt with by some eyes.
Yeah, you can think of this lambda as the AI as being eyes, like in the usual ordinary. Let's say you have a U1 theory. Okay, the covariant derivative should really have an I, right? Because it's e to the power I beta. And
So do you have that I?
yeah, I would have that I. So really IA is the real field. Yeah, this would become important in a moment. So the point is that I just don't want to keep track of various I's. Okay. So the point is that so this guy, let me call it as 0 algebra. So I would say that any field which transforms this way is in the 0 algebra representation of thermal translations. This will become clearer. Okay. One thing you can do is you can generalize this. Okay. By saying that something like this. In general, you can make a del beta. And then you can have image. So what you can do is that you can introduce a kind of an inhomogeneous transformation which involves derivative of lambda. Okay.
No, what is zero and representation that
Lambda is just a parameter.
Parameter of this.
Sorry.
zero representation? What is that?
This is the definition. A field on which the thermal bracket, let's say this, acts like this. That is, the thermal translations act by just the usual in the most intuitive way, lambda beta dot del phi. Okay. But what I'm saying is that you can also consider this kind of representations where this thing, and you can show that this is a representation. Okay. And in fact, the k equal to 1 is what you would call as an adjoint representation, in the sense that the lambda lies in the adjoint representation. Okay. And in general, you have this I call it as a k adjoint. Of thermal translations.
Look, I'm still struggling to find a familiar analogy. Okay, so suppose we just had spatial compactifications on a circle, and the size of the circle, varies, its direction varies. Is there any familiar situation in which I've just got a scalar field theory moving on some? Is there some sense in which I've got a new gauge field in that problem?
So you have so you have the Kurzgesagt modes of the scalar field.
Yes.
Okay. And there's a Kurzgesagt charge associated with it.
Yes.
Okay. And you can think and those charges, you can associate it as discrete gauge field.
You can associate it with discrete. Is this any more than a bookkeeping device to keep track of periodicity? Is there more of it? Can I do it without this gauge field? Just keep track of periodicity.
But in the real time, there is no periodicity.
So in the case of the scalar on a circle, I will never.
So the Euclidean field theory, of course, just periodicity.
Right.
Okay. The real question is what happens if you analytically continue.
Okay.
Okay. The correlators. Okay. How do you reproduce the real time correlators? Okay. And how do you reproduce the constraints that if you went to the Euclidean theory, there is a periodicity.
Okay.
Okay. And how do you move away from it? How you deform away from it. Let's say if you're not in Euclidean. See, if you're in equilibrium, you can just recrotate, go to the Euclidean theory, and you have this. Right? Okay, if you're not in equilibrium, okay, then what are the constraints on there are constraints because you can think of this as a deformation of the thermal state.
Yes.
Okay, by adding sources and so on and so forth. So it's just like thermal state with some additional insertions of operators. Okay, and it has constraints. And the question is that how do you take care of the constraints and how do you write down a theory which automatically satisfies those constraints? These are the KMS constraints that I was talking about yesterday.
So are you saying that it's obvious that this is the right thing to do, or is this a proposal that you will check process tests?
So one
doesn't
thing
seem obvious to me somehow. Yeah.
So the one thing that I did show yesterday was that that at least in the scalar theory, okay, it works like that. Okay, and in fact,
Is there a kinetic term for this gauge field?
Yes. So I would there is a kinetic term for the gauge field, but I won't be talking about the dynamics of the gauge field today. Okay. But so I mean, if it is too bothering you, okay, for this talk, we'll just assume that it's not dynamic.
Not dynamic.
Okay. But it's just some background source. Okay, it's a background gauge field.
Background gauge field just keeps track of the temperature and velocity.
Yeah, temperature, velocity, and entropy, current, and so on and so forth. Okay. Okay. Though it has some issues, but you can just let's say. I don't want to get into that. So we can just assume it's the background gauge field. So it's just gauging by background gauge field. Keep track of these things. Okay. So the question is that so you can introduce this clear joint representations, and you can do this representation theory. For example, you can say that you can introduce, for example, phi is a K joint. Okay. Then L beta phi is actually a K plus 1 joint. Okay. Which you can just check by the definition that I gave.
K is an integer.
Yeah. K is an integer. Okay, so this is a property. Okay, there's another property which is also true that 1 plus beta of A is a 1 joint. These are all some set of properties which you can use.
Okay. So these K joint guys are higher and higher Kanizak line nodes with charges K. Is that?
I probably, but you can, yeah. But we haven't quite managed to pin that down to that. But you can just, but probably.
Sorry, just one more thing about this gauge field. You're gauging. I don't even quite understand how you're doing it, but your words are that you're gauging these imaginary translations in time, and in the mathematics you're not gauging discretely, you're gauging continuously. So if you were really doing that, you would be ensuring that the function was constant in imaginary time, and therefore would just be constant always.
It would be if there are no other fields which are charged. I mean, it's like putting a Gauss constraint. Okay. So the Gauss constraint, you would think it gives you just completely chargeless guys. Okay. But and that is true if there are no charged particles. But all the fields are charged under it, which means that various things can cancel.
So I'm still not understanding. If this whole thing is to impose that arbitrary translations in imaginary time are unphysical, then surely the analytic continuation of that is that arbitrary translations in real time are also unphysical.
With this gauge field. So
no, but when you gauge something, you impose it on the whole system, not on the other gauge field.
Yes, indeed. So, but if you didn't have a gauge field and if you impose something like a Gauss constraint, you would get that something is invariant. But there are the fact that there is a gauge field means that in some sense this is deconfined.
The gauge field eats up some of that. Yes.
Yeah. So okay. So now you come back why the reason why we need to make it dynamic. But anyway, but never mind. But the point is that so you can do the representation theory of this. So there are like some nice facts like this. Okay, which you can use. Okay, and the reason that I'm saying all this is that so you can take the scalar theory again. So let's integral over z, which is both sigma a and theta. Okay, so and to this you can add, as I was adding yesterday, something like d theta phi, d theta bar phi. It's a meter. Okay. Okay. And with d theta involving all these covariant derivatives, and what you have to do is that you have to write down a theory which has the invariances of various things. Okay. So that is the basic idea. Okay, and what I'm going to do in the rest of my talk is to apply this idea to fluid dynamics. Okay, so to say again, so.
I'm so sorry. I have to try to understand. So the original field theory, fields were phi L and phi R. That's it. And in the Euclidean theory, there was a number called the temperature. Now we are doing hydrodynamics. That means in a local patch of space-time, it is like the temperature is constant for this patch. Another place, temperature is constant. We're trying to somehow compare these temperatures, and the natural way of doing it is by a gauge field, by some sort of a connection. Is that's what's happening? Looks like. Why you're doing it, I don't understand. But is that correct? What I'm saying? At least
I'm not entirely sure, but I have to think about it.
Because now you're going to say that I'm going to apply all this to hydrodynamics, which we sort of understand. That temperature is locally constant in equilibrium, and the temperature here and the other side of the room, they can be different.
But first of all, the temperature, even in hydrostatic, the temperature can vary. You can just you can take a Euclidean path integral with just time the varying circle.
Yes. So that's a time independent situation of the hydrodynamic equations. I agree with you.
Yeah.
But,
So
aren't you trying to compare the temperature at point X and point Y? In some sense.
I mean, the temperature is the point X and point Y. So temperature is a vector, for me, beta A. It's a vector field, it's a triangular vector field. Now,
so you're trying to gauge that, really. Basically,
I'm not quite trying to gauge that. I mean,
you're trying to gauge the symmetry generated.
In fact, beta is. Beta itself is invariant, and for lambda comma beta, it's actually 0. It's just legal beta. Okay. So anyway, so right. Sorry. Okay. So you can add a term like this, and just.
So just before we get to hydrodynamics, let me understand what good thing happens with this action.
Yes.
So with this action, first of all, shall I think of this as the action governing, the dynamics of the water parameter of the Ising model and space transition, right?
Yeah, the leading dynamics, of course, you have additional terms.
And this action somehow encodes the fluctuations
and dissipations
of this field. And what else could you add to this action? You can add a potential.
You can add a potential.
And you can add higher derivative terms.
You can add higher derivative terms. You can add, in general, you can take the general lambda Ginsburg theory, and you can feed it here. You can add some dissipation. You can make this a function of phi.
And does this match with something else, type A, type B, type C, that I keep hearing about in the dense matter?
Yeah, so it will match with the. Okay, so in this case, it will match with the Hornberg-Halperin. It will be nice to understand the complete Hornberg-Halperin, how it looks like. But yeah.
It matches in detail. You get some sort of gradient flow along.
See the Hornberg-Halperin involves, an assumption of the gradient flow and a linear dissipation at a Gaussian pulse. Okay.
So there is a particular action of your form that will give you.
Yeah, so basically you just need to have only quadratic terms where beta is not dependent on anything, it's just a constant. Okay, which should give you what you want.
Where is the gradient flow?
The gradient flow. The gradient flow is the gradient of this guy, which is the when you vary.
That's just space. But there's also double time there. Oh, you take this large friction limit in the gradient flow.
Sorry, what? So you ask, okay. I mean, okay. I understand what you're saying. So if it's a non-relativistic theory, okay, you can add something like phi diagonal phi. I think, and then
which I can think of as just like a large friction.
On the non-relativistic.
But in your model, if I take eta larger, somehow eta dominates over the kinetic term. Yeah, okay, I understand. You want to keep spatial variance but not time. It's fine.
Okay, which will be non-relativistic. Okay, so the question is that so there's another thing which is often which also let me talk about before I go to the fluid dynamics, which is about CPT. How the CPT.
So what I'm understanding from that is that Moenberg-Halperin is one particular example of many possibilities, and it's written down completely arbitrarily. You could have modified it in many ways. Nothing particular is secret.
Yeah.
Should I take that as a lesson?
That was universality.
That I should take that paper too seriously?
You should not take that as a it's a good starting point. That is the lesson that you should take, that you should not,
Is there an argument that the terms which he is referring to are not relevant actually for him?
There's some very...
Actually, you should ask Rajdeep these questions because he's doing something where he sees non-consumer. But anyway, the point is that, it's a good starting point. It's like,
saying it's a deep IR element. Some particular level where you scale time to infinity in a different way from space or something. Other things go away. Like Navier-Stokes equation.
I've never found this argument to be, I've never found an argument of this sort.
Okay.
It could be that, you can justify the Gaussian noise, but usually, as far as I understand it is justified that it's the simplest thing. Okay. Which is, of course, the first thing you should do. Right? You can have a system at your hands, where you have to add more terms. For that, you need to do a proper effective theory. Okay. And so, the various terms that you can add. So one constraint on that is CPT. Okay. So the CPT, acts in the usual way. I will not say so sigma A, sigma A. Okay. And in the Schwinger-Keldysh, it also acts by exchanging right and left. Okay. So and you can think about it, but this means that you should end up exchanging theta bar also. Okay. So CPT acts like a R parity on these theta fields. Okay. So and of course you can have some intrinsic parity also. So you should impose an invariance, and then of course the anti-unitarity, it acts anti-unitarity. Okay, that's it. Okay, so
if I set by difference phi to 0, then the equation of motion will be del squared phi plus phi dot is equal to 0 plus eta phi dot is equal to 0.
In the equation of motion.
Yeah, I just want to see what classical equation of motion I get here. Is it del squared phi plus eta phi dot is equal to 0?
Yeah, eta beta dot del phi.
Yeah.
Okay, good. So the point is that for the CPT and maybe there's some other symmetries that you want to take care of, and you get okay. So let me apply to fluid dynamics. So for that, I have to describe the Landau-Ginzburg theory of fluid dynamics, which let me try to do it quickly because you have heard this. Before.
You should assume we've understood it.
Okay. So I'm going to implement the strategy that I just outlined. That is, you start with Landau-Ginzburg theory, which gets a statics right. Then you go to superspace, which gets a doubling right, and topological limit right, and then you gauge the theory with the thermal translations to get the thermality right, the fluctuation distributions. Okay. So this is the strategy. So Landau-Ginzburg of relativistic fluid dynamics. Okay. So the But the dynamical field,
Sorry, one last question. The equation of motion that I talked about, setting the fluctuation fields to zero, is that equation of motion precisely what will allow you to find retarded correlators in that theory? And you can't use it for
within retarded boundary condition.
Yes.
You solve the equation.
But what I'm saying is the noise can decouples from that question.
No, you can't quite. I mean, yeah, maybe in this case you can, but in general you can't quite just decouple the noise.
But just at quadratic level.
At quadratic level, you can probably decouple it.
So we can compute the retarded correlator just as a solution to the equation of motion. Of this solution, the solution to this equation of motion. And
the leading order.
The leading order what?
This quadratic.
Yeah. And then now you have a way to compute all other correlators. Right? Time order correlators. Fine. And okay, with that, because it's all quadratic,
and you can differentiate with respect to the difference source and so on and so forth. You can deform away from the aligned limit, and you can do various things. Yeah. Anyway, but the point is this. So I'm going to think about the Landau-Ginzburg theory of relativistic fluid dynamics. And here the field that you're interested in is just beta mu, in some sense. Okay, which you can think of it as some flow velocity. Okay, by temperature, and the flow velocity is -1. So really this beta mu carries the whole information about it. So its modulus carries the information about the temperature, and its direction is time and velocity, the velocity of the fluid. So you just have a fluid with no conserved charges, no chemical potentials. So this is the simplest system. Okay.
Logan, we have to warn you, there's a class at 11:30.
Yeah. Okay. So the source for this background source is some G mu, okay, and so this is the background metric, okay, and there is a corresponding current which is T mu, okay, and your equation of motion of the relativistic fluid dynamics is that carrying T mu equal to 0, which is this conservation of energy, okay. So the question is that and of course like in the usual fluid dynamics you will also import that exists a Js. So is that divergence of Js is greater than or equal to 0, where Js is also a function of beta and G. So these guys are functions of beta and G, this is also a function of beta and G. Okay. Some local function, so some derivative expansion. And this is the standard definition of the relativistic fluid dynamics, if you wish. Okay. That you have this field and so on and so forth, and this is what we want to reproduce. Okay. Good. So how do you start writing down the Landau-Ginzburg theory? So one of the most important things in realizing how to write down Landau-Ginzburg theory of this kind of a system is to realize that beta mu, these fields that we have talked about, should not be thought of as the elementary fields, but we should think of these as the composite fields. And the way you do it, okay, is something like this. So let us say this is your space-time, in which the fluid lives. So there's a beta mu there. Okay, and then there's a G mu. Okay. Now you take another copy of the space time. Okay, let me call it M, or let's say space filling ring. But it's basically another copy of the space time. Okay, and And I think of this beta mu as actually coming by a beta in this other copy. Okay. So what I have is that so I have another copy of space-time, and let's say I also have so in this is the space-time is sigma A, and this is x mu, and I have a mapping which is x mu of sigma A, an invertible mapping, okay, which maps points in this M to the space-time.
Beta is a fixed vector field.
Yeah. So now what I'm going to do is that I'm going to take a beta A in this fictitious copy in this brain or in this world sheet in the world, if you wish, and I want to make this beta A as non-dynamical. Okay. And I want to think of this as a dynamical field. This mapping between the points is the dynamical content of the theory. Okay. And beta mu is basically beta A del A x mu.
J depends on sigma.
Yeah. Okay. Okay. And using this x mu, you can also take, you can bring the metrics on the spaceline to this M. Okay. So there are various choices that you have. Okay. So let me take one choice. So the point is that the way to think about it is that the beta mu is of course a dynamical field. Okay. In the free dynamics problem, and you think of those dynamics as basically coming from a fixed field and a dynamical mapping. Okay. Or often it is also convenient to go to the just work within M. In which case you think of beta A as the fixed field and GAB as dynamical, because GAB involves also the x mu. Okay, so this GAB is just G mu del A x mu del B x mu. Okay. And it involves x mu, so you can take this viewpoint, and this is the viewpoint I take, where I think of beta A as a non-dynamical field, and this is a dynamical field. So this beta A is non-dynamical, this G mu is non-dynamical, this beta mu is dynamical, and so is this script G. Okay, and the dynamics is basically coming from the fields which map. Okay, so this looks like a very complicated construction, but this is exactly the construction which gives you the equations of motion that you want. Okay, so what you can do is that you can just write down a Landau-Ginzburg theory to start with, by just taking d to the pi d sigma and some Lagrangian, which is a function of this non-dynamical field beta and the dynamical metric field G. Okay, where the dynamics is this.
And you make it differentiable.
And you make it differentiable invariant and so on. And the point is that this reproduces, okay, to a large extent the
square root G that function of length of beta will be the simplest.
Yeah.
Or that would be
a function of the length of beta. So
that would be perfect fluid.
Yeah. So the perfect fluid dynamics is just this taking with no derivatives. You take P of beta, okay, where P is the pressure function, P is the mod beta. The mod is taken with this G. Okay. So the mod beta is also dynamical. Okay. Then you can write down the pressure function, you can vary it and so on. And this is the correct statics. The most part.
So all this you say is exactly equivalent to Nicholas' zone, blah blah blah. It's some new language for Nicholas zone.
I would say Nicholas zone was gravity, but more Dubovsky
and Nicholas. Well, yeah, exactly,
Dubovsky and also people before them. It's a old subject. There are various ways of doing this, and just doing a particular way of writing down the non-distributed fluid dynamics. So this reproduces the Euler equation. If you take the pressure function.
One thing that seems different between what they did and what you did is that you have time diffeomorphisms that have times. They have only spatial.
Yeah, but I have a fixed vector. So kind of
you can use that time diffeomorphism to set that or something.
Yeah. So you can show that this is equivalent in various ways. All different Landau-Ginzburg theories that you can write on fluid dynamics are all the same. It's just that I prefer this because it's easier to do.
It's very good.
Okay. So you can get the Euler equation, and what you can do is so you just have you vary with respect to x mu. The x mu's are all sitting inside G. Okay, and the way you get it is that then you get something like grad of whatever you get by varying GAB.
That's obviously conservation stress.
Okay, and GAB. So what you can do is to get the dynamics here, the dynamics is sitting entirely inside the metric, because the x's are sitting only inside the metric. So you first vary with respect to G, okay, and then in the variation of G you do an additional derivative. You do a derivative, and the derivative is covariant derivative. You can go through this. So the point is that whatever action that you write down, the equations of motion are exactly the conservation equations for the energy momentum tensor, which is what you would consider the usual energy momentum tensor. Okay. Good. So we have an Landau-Ginzburg theory.
Wait, though you think of your fluid as living on the upper space.
Yes.
Now you've got a conservation equation on the lower space.
translate,
If you're possible.
yeah, you can just push everything, back and forth.
So you dynamically calculate the x mu's and the GAV.
X mu,
Only X.
only X mu. TAB is a function of that.
Wait. So
TAB, GAV, everything is a function of that.
GAV, no. Out of let's say that I am fixing beta A to be some fixed guy.
Yes.
And beta mu, of course, is then determined by the embedding.
Yeah.
Okay, it's mu sigma. And in case of G, what am I doing?
The G union is fixed. It's given to you. It's the space in which let's say if you're on if you're modeling motions, it's just the metric on the.
So GAV is determined by.
Again by
that. So only x mu will be that. So.
Okay. And if you vary with respect to that, the dynamical theory, you get the conservation condition. So this is the correct theory. That with the correct degrees of freedom. Okay. And so it's the correct theory for our strategy to go. Okay.
This is extremely good. This is really nice.
So you get the dissipation also.
Not yet. No, we're just looking at the analogism of theory at this point. Okay. So then the next thing is to go to superspace. Okay. And which just means that you just interpret all these indices as super indices. Okay. So all indices are super indices. Okay. And you can basically, the d to the power d sigma will get a d square theta, okay, and everything works as it is. Okay. I mean, there's not much there to be said. There's a lot of signs, which you keep track of when you take a Gassman-Hort guy, but that's all some technicality. Okay. So then let me go to the third issue. So we know this thing. So you have so these are all super fields. Here these are now super fields. Okay. Yeah. Okay. Good. So now the next thing is to make it be fluctuation dissipation, to bring more thermality, which is to gauge thermal transmissions. Okay. And the way you do it is to basically convert all the derivatives, okay, to like it is a gauge field. Okay. It's often convenient to gauge fix it such that beta does not have any component other than A and so on. You see the few more steps, but yeah. So you can just do this. So what you have to do is this thing, and there's something else that you need to do. Okay, to gauge it correctly, because this G also contains. For example, you should put this pullback also in a consistent way. So in fact, you have to write DA as rather than writing the DA in DA, you have to kind of make it into a covariant derivative. Okay, and this has the effect that if you actually pull back the measure, the ordinary measure, square root minus g, this doesn't quite pull back to square root minus g, but it must pull back to square root minus g plus 1 plus beta dot a. So this is the measure that you should use. This is the U1T invariant measure. This is the thermal invariant measure. So yeah. So these are the things that you have to do. So this thermal gauging, the thermal invariance, is in terms of the non-trivial stuff. This is just a matter of super spacing everything and then keeping track of signs. But here, there's some, we have to be very careful about what are the representations that you write down and how do you write down the correct Lagrangian, which is invariant under all the symmetries in the problem. But if you use this measure, you can show that, basically if you write down some action like d to the power d sigma, d square theta, this measure times some Lagrangian, which is in 0 joint. Okay. Then this action is U1T invariant. or basically thermodynamics. So,
What is your UNT transformation?
the dx mu is just del x mu plus ax mu beta delta. In general, you have to do it with the thermal bracket, which I defined.
Okay.
So the statement is that if you take a lambda, in general space-time dependent lambda, then if you do like lambda comma, let's say this guy, then this is the layer.
Just remind lambda, how did it act?
It just acts like this. So this is basically AI comma x. It just acts like common transmission.
And it just moves x with an I?
Lambda is imaginary. Okay.
So just motion in the direction.
Yeah.
So 1 plus beta A is some kind of square root of chi factor in the Euclidean time direction. Is that why it comes? Or
So here it just comes because like you're doing a covariant pullback. Thermally, you're not pulling back with delta x mu. Okay, so the delta x mu and dx mu, they are Jacobians, have a ratio which is 1 plus beta over A. So which you have to take care of. So that you're correctly pulling back the measure on the physical space time. Okay, and when you do that, like you also get the correct invariance. Okay. So now what you can do is that you can add the let's say the pressure term that I written down. Okay, so there's this equality to b to the power z. Okay, so the integral of z. Okay, which I already had. Okay, okay, and then like to this you can add something like this. Exactly like what you did in the scalar theory. Okay. This I you can check use it for CPT variance and so on. Yeah. So this A, B, C. The CPT invariance actually forces the ABCD to be the CPT invariance. So you can write down this guy, okay, and you can again go to like you can take the background where you have A theta going like theta bar and A theta bar going like theta, okay, or just one of them going like theta bar, theta half something, and then you can just evaluate, and you can evaluate again delta x by delta x mu equal to 0, okay, and you can show that this reproduces discrete. Okay.
Which means GAB is dynamical.
Yes.
To the x's. Can I write down some Ricci scalar term? All types of things that can be done.
Yeah. You can do that. Yes. In fact, you do that. When you go to second order, you write down the Ricci scalar, which leads to some second order non-dissipative dynamics. I mean, one thing you have to do. Okay. One thing you have to do is take in the Landau Ginsburg theory, you can do that. Okay. So here, when you introduce this UNT, there are some subtleties with respect to doing that in a UNT covariant way. You have to define that in a UNT covariant way. But since I'm running out of time, let me not go into the technicalities. But this is the basic idea. So what the statement is that that you have these fields, okay, which gave me the Landau Ginsburg theory, which is just right, and you can go into superspace and you can gauge it. Okay, and write down this action and vary it and get this hydro. And the nice thing about it is that like because of the supersymmetry and so on and so forth, this very simple construction, okay, basically takes care of the basic constraints of the Schwinger-Keldysh. So all correlator that you calculate, okay, with this, for example, being weighed and the Schwinger-Keldysh.
If I just think of A and A bar background fields set to these values, the actual is supersymmetric?
No, because it's like a Weismuller. Yeah, so you have to, if you do it, changes by a gauge transformation. It's like there's no bridge.
Okay. So it's necessary that A and A bar are dynamic for this statement. So then you have to tell us something about the dynamics of A and A bar.
Which I don't I'm not going to say. The point is that the dynamics. See, the dynamics should allow this background. So what is this background? And gauge invariant way of saying this background is that f theta bar. Okay. F theta bar. Again, if theta bar should be 1. Okay.
What identities of this gauge invariance?
Yeah, so very important that they should impose the correct thermal gauge invariance. They impose the correct fluctuation distribution. Okay, so what I was saying. So this is really the physical way of saying it, because this is a difference of the gauge. But what you have is that that you're giving a value to this f theta bar, okay, which is a particular it's a particular nice object in the joint of this thermal invariance, and this is the important thing. Okay. So that is the statement. The statement is that that you are in the background where you have this guy. You do get this. So, provided I'm not going to tell you about the dynamics, except that I'm assuming that the dynamics allows me to say. Okay. Okay. So that was a bit too fast, but anyway. Yes, as I said, this kind of thing. So this is what you do. And so let me just conclude by just summarizing these things. So what we were saying was we are trying to at the beginning I do these 3 boxes, okay, which were like the Schwinger-Keldysh rules in the back. Okay, and in this in this whole setup. Okay, so what I was trying to describe is that that there are various ideas in Schwinger-Keldysh. Okay, and black holes. Okay, that are very closely related because of various statements. Okay, and what I have just described is a kind of at least in my mind, it's the simplest proposal which realizes the various statements that I was telling you yesterday. Okay, for example, the statement that you should really be thinking of thermal invariance as symmetry, and so actually this action you can also take delta S by delta A, okay, and you can show that gives you the entropy current. Okay. So that this gives you the entropy current. Okay. So that the thermal invariance gives you the current associated with it is the entropy current. There's a dissipation, okay, and the dissipation can be written in this topological field theory language. Okay, for that we used these various statements that I had mentioned in yesterday about how you can try to write down some superspace action or some action with some cohomology Q and Q bar. Okay, some such that it exactly localizes to the particular set of solutions that you're interested in.
Since the entropy current is not conserved, it means that the gauge invariance is broken.
Well,
because if I impose gauge invariance to a coupling like A dot J, then it will be conserved. And
well,
if it is not conserved, then that symmetry is not.
So what is not conserved is the matter part of the entropy current. Okay. So the question is about what is coupled to the whole thing, and also you have a wave. So this realizes, by the way, so a year ago I was here, I was talking about trying to double the theory and think about this viewpoint invariance and so on and so forth, how it is imposed in terms of some Higgsing of a particular Higgsing, and in some sense this is the thing, because this theta bar is a one adjoint, it's not quite uncharged. Okay, and we are giving it a wave. Okay, so this is the particular theory. Okay, so you can calculate the entropy current here, and you can show that the Boffonic or the Grassmann even part of it, okay, does match with whatever you usually have. It just has additional cores, and these additional fields, like when you put dynamics.
So it is true that this gauge symmetry is, in some sense, local because the intrinsic element is not conserved.
It is broken. In the usual sense. In this sense. In this sense, So what in the sense that I've written. Okay, so these are the assumptions that we make, that we look at this condensate of f theta theta bar. So in some sense, this is like studying the theory in this background. Okay. So usually it doesn't. So if you just turn on a background field strength, so if you think of this as some U1 theory, like turning on such a background field strength does not, break gauge invariance. Okay, but this is not quite a U1. It's kind of a U1 with some non-commutativity. Okay, in the sense that this guy is non-commutative. Okay. Okay, so the point is that you have so what I was thinking about, because this Schwinger-Keldysh is a black hole, okay, and what this realizes is these various statements that I made, okay, in the thing. So just to say, so there was doubling, okay, and there was thermal invariance on the Schwinger-Keldysh side. These were the important things. There was dissipation on the fluid side. Okay. There was entropy current, which is related to that. Okay. And second law, and fluctuation dissipation theorem, and fluctuation relations like Jarzynski. And what this formalism does is that it kind of puts them all together, and it kind of makes all the statements consistent. So it's very natural to proceed and say that like the various things about the black holes, which are not addressed, which remind you, was basically to do with horizons in the interior and black hole complementarity. Okay. So one of the main motivations for us to understand this in a detailed way is that so this is a system which we understand very well, phenomenologically, and if you just understand how the doubling works and how the ghosts work and and so on, then and if you accept that this is the way that fluid dynamics should be thought about, okay, in the field theory, then it follows that if ADS-CFT that that there should be a corresponding feature in the black hole side. Okay, for example, there should be a corresponding statement to this that there's a condensate. Okay, and that is behind dissipation and so on. Okay, so of course I don't have much more to say about black holes except to say that what I've said before, which is about OSV and so on and so forth. That there are reasons to believe that black holes do satisfy this kind of picture. One, because of OSV, which says that there's a double topological theory which does describe black holes. Double topological theory does describe black holes correctly, at least in a particular regime. And another because of Wald, okay, where this statement that the thermal invariance and the current associated with that gives you the correct black hole entropy. Okay, so both of them say that these various things that enter into this formalism are very natural to think about in the black hole context. Okay, so with that, let me thank you for your patience and thank you.
So, the original work of Shiraz and collaborators basically said that you can understand the velocity as a collective coordinate actually on the horizon. And, the hologram is the fluid dynamics equations. Now, by what you have said, would it be natural to somehow say that, in a sense, in some sense, these additional degrees of freedom actually which account, especially the supersymmetrization which is related to the dissipation, can be understood as fields that live on the horizon also? I mean, I'm not saying anything new beyond what you said, but can we say something more about it in this way?
Yeah, I don't know. There's this Nicholson proposal, okay, which in our picture would translate to saying that say the x mu are actually fields which go from the boundary to the horizon, okay. But the point is that nobody has made it to work. I mean, all of us have tried. Various, have tried. The tidal fluid is fine. The dissipation you can kind of fudge. But higher derivatives, it becomes quite an issue. It's not clear what one should do. Okay. It's not to say that it's the wrong idea. Okay, it's probably the right idea, but I'm just saying that none of us know how to implement it correctly.
So, in that point of view, sigmas parameterize the horizon of the black hole, and x mu of sigma is this map.
Yeah. Somehow the beta is the But I mean, these are all nice statements, but the question is to make it work. Okay. And also make it work in such a way that it's consistent with both WAD and OSV. Various things that we know about OSV. It's not, I mean, one cannot just say and go and propose something, because we know that they're we don't quite know how to implement it. But if you give me an implementation, I know various ways to check that implementation is correct. And also, it should also, in some natural sense, realize if you believe in what Subrat and Kireko say about how you should think about the interior, you should somehow naturally reproduce those statements about how to think about the operators in the interior. So these are very strong constraints. If you really want to implement it. And
if I'm doing calculations around the thermal background, there should be some sense in which I can think of this theory as a theory of sound modes and shear modes. And one of the results of one of the consequences of what we've done is that you should be able to tell me what Feynman rules I should use for the sound modes and shear modes to compute, for instance, contour order coordinators. So, is that easy to do?
So we haven't done that, but it is implicit in the way we are considering. So the sound modes and shear modes are sitting inside X mu, after to take care of all the invariances and so on. Okay, and so I have an action, which means that in principle one should be able to write on the Feynman rules. It's a complicated action.
Right. It would be nice to interpret the Feynman, the vertices directly in terms of the equation, of the hydrodynamic equations.
Which is the case here, because all the coefficients which occur in my action are
related to hydrodynamic coefficients. But it would be nice to just think of it as a 3-point function. Can we all think for the retarded correlator, all the 3-point functions are those that appear in the classical hydrodynamic.
Yeah, I would say for any correlator.
So, I'd like to know how that works. What is the effective set of rules? So you're telling me that
this is a nonlinear Lagrangian. So the the effective set of rules it will look like the Feynman rules for gravity or something, where you will have like arbitrary point functions and so on.
Excellent. But each of these effective Lagrangians should each of these arbitrary point functions. Oh, you're saying that even though that's fine. But each of these at least for the retard correlator, I can think of that as just taking the nonlinear equation of hydrodynamics and expanding that in amplitudes of the shear.
So you can linearize this fraction.
Okay. Yeah. So
and you can see whatever you get. It's what you get. I mean, it will look horrible, but it's whatever you get.
But there would be some nice effective rules for.
Yeah, there are effective rules which you can read off on the. I mean, what I'm saying that there's an action. I mean, if you want the Feynman rules, you have to linearize and write down all the Feynman rules, which you can do.
Yeah. So, but wouldn't it be nice of me to have a set of rules that given the prescription, given an equation of fluid dynamics, from there to get the rules.
Yeah. So, given an equation of fluid dynamics, you can write an action. So, this action gives you the rules.
I understand. It would be nice to have a more direct translation. For instance, for retarded coordinators, all you have to do is to couple the source and find the response using the equations of mathematics. So you don't need to go through all of this.
Yeah, but the point is that like if you want to get the other things in a correct analytic continuation, okay, you need to have all these goals and if you're not like.
So is the time-ordered guy? So one way of saying it would be just to find the right analytic continuation of what I just said.
Yeah, but analytic continuation, see, fluid dynamics is a derivative expansion. Okay, analytic continuation in such expansions are almost impossible because especially because the thing that you're analytically continuing with is the thing that you're expanding about, which is beta. Okay, so especially if you're doing a small beta expansion, okay, to analytically continue that is like you have to like resum the entire.
Why are you doing your analytic continuation? You're not analytically continuing in beta, you're analytically continuing across some omega.
Yeah, but the point is that like then you have to keep track of the beta. Like they become exponentials and the exponentials go and move away. Some exponential I betas become exponential betas and so on and so forth.
Okay.
So if you just have 1 plus I beta,
you don't know what it was.
Yeah, I don't know what it was. It's okay if it is hydrostatic. Okay, where like everything is reduced.
So but then maybe your rules will give me an effective way of doing this analytic continuation.
Yeah, so that is another way of thinking about this, that that whenever you analytically continue, for example, when you analytically continue Chern-Simons theory, okay, one of the things that we can argue is that the nicest way to do it is to add ghosts, okay, and first of all do it in one dimension higher, like with the space-time is the boundary of, and think of, like write down a twisted n equal to 4 Yang-Mills, so that there are ghosts and so on and so forth, which exactly, like choose the particular contour in which you are analytically continuing to. Okay, so another way of saying of these, all these adding the ghosts and so on and so forth is that this is you take the Euclidean path integral, which say just P of beta, okay, and you analytically continue it, and in analytically continuing, okay, you have to introduce ghosts and so on and so forth, so that you choose the correct contour, okay, and when you choose the Schwinger-Keldysh contour and so on, this is the way to do it. This is what you will end up. So you can just forget about maybe if the Schwinger-Keldysh and so on and so forth, like you just say this is just mathematical statement of analytical continuation of Euclidean path integral.
Right.
Okay. And it is known, at least in this Witten's work, that that kind of thing does introduce ghosts, gives things like this. Okay. Of course, Witten worked it in a very simple theory, or very nice theory, not a simple theory, but in Chern-Simons theory. Okay. In 3 dimensions. But in principle, you can think of doing that. Okay. And though you can't do it in practice, like it gives this kind of stuff. At least when you can do it.
What is the propagator that you use for? The usual Feynman propagator has this effective boundary condition that you have that in the future you have only the dissipative solutions, and the past you have only the anti-dissipative solutions.
If you, the dissipative and anti-dissipative quite don't. They're not. It's exactly what I said, which is that if the difference leads to 0, it gives you whatever it gives you, and it could give you the dissipative solutions are.
Will it blow? I'm asking whether your propagator blows up. You see, your solutions to your equations of motion have both dissipation and anti-dissipation. If you look at all the linearized solutions to the action, whenever you've got an action, if you've got a solution which decays, you've also got a solution that blows up.
Well, I think see this guy, for example, breaks this.
The boundary condition that phi q is 0 at very late times do not let you have the rising solution.
That's what I was asking. So I was asking if the effective boundary conditions are that the anti-dissipative solution vanishes in the future and the dissipative solution vanishes.
At least in the past.
The next statement I don't know. The first statement.
Well, it has a time reverse of the earlier.
Yeah, it's okay.
So you say that's what I'm taking from you. So the Feynman correlator propagator I could think of as a solution to some equations with these boundary conditions, and then I use these correlators with an appropriate 3-point function to get all the correlators. Okay, thanks. One more question along these lines. Okay. Is it exactly true that retardant correlators can be computed using only just by classical hydrodynamic equations, or are there noise corrections?
At least at this level, okay, you can show that all the noises that you get, you can do a Hubbard-Shuttlenovich like I was saying, and convert it into Gaussian noise.
Wait, that's the noise part. I mean, is the statement that, so what I'm saying is that if I want to compute one response, I want to compute one response as a function of various sources. I know how to do that in hydrodynamics. I just compute the response and expand it as a nonlinear function in sources. That object is some correlation function. I want to know whether that's exact or gets corrected.
So the noise does corrections, but the point is that the noise, because it's a base fluctuation dissipation, okay, its corrections are suppressed in N. So the equations, if you just solve them, then classically, like you would get something, but it will, like if eta has an n square, eta has an n.
So overall coefficient outside the action is your n?
Yeah, you can say. More importantly, eta, because like roughly the noise goes like 1 over eta.
Well, in an ADS or a large n situation, the pressure will also, both would be order n square.
Yeah, both will be order n square, but what I'm saying that in this, the way it works is that this fluctuation dissipation forces something like this. Okay. If the noise.
Well, can I think of just putting an n square outside the action, and then if you just do classical analysis with your action will exactly reproduce what I said.
No, it will reproduce it with 1 over n square. See, the classical itself can give you 1 over n square, right? Because of this.
Well, I'm taking an n square overall outside the action.
No, but okay. So the point is that you have to do when you do a Hubbard-Shuttlenovich.
Let me do nothing else. I'm doing n equals y angles. It's true, right, that the action has an overall n square outside the action.
It's true that its action has overall.
And there's no other appearance of it.
Yeah, but then there is the phi average, right? You have to. The point
Phi average is part of your.
phi difference.
One of the dynamical fields. I've just got n square outside, and I've got an action. Now I do classical physics with that action.
Okay, so that would be just taking everything to the expression. So noise you just set to 0.
Yeah.
Okay.
That could, I think, would reproduce exactly, right? Okay.
That's just setting everything to its expectation, right? So including the noise.
Yeah, I think.